We will now talk about greedy algorithms as an algorithm design technique for solving several problems. I will be mainly focusing on optimization problems. Okay, so we will talk about greedy algorithms. Again, this is an algorithm design technique, and I will be mainly focusing on optimization problems. And an optimization problem is a problem where we are seeking a solution that optimizes a function, either minimizes a function or maximizes a function. So for example, the shortest path problem in graph is an optimization problem because we are looking for a path that has the shortest weight or is the smallest length. Minimum spanning tree is also an optimization problem. We are looking for a spanning tree whose weight is minimum among all possible spanning trees, and so on. Okay, so an optimization problem, usually we see the problem as the input is some structure and the output is something about that structure that maximizes or minimizes a function. Okay, and a greedy algorithm, basically, when we talk about greedy algorithm, it builds the solution to the problem piece by piece. Okay, what I mean by this is that if I am looking for a minimum spanning tree, for example, I start building that tree one branch at a time. If I'm looking for the shortest path from node A to node B in the graph, I start building that path one edge at a time. If I am looking for finding some structure in a graph that optimizes different function, we start building that structure one step at a time. Okay, so we build the solution piece by piece, and when we are choosing the next piece to add to the solution, we basically choose, in the case of optimization, we choose the optimal piece that's available to us. So the second component or ingredient of a greedy algorithm is that when we choose the next piece, to be the locally optimal among the available pieces. Okay, so if I'm building again the minimum spanning tree and I have already built some subtree and I want to add one more edge to it, I look at all the edges that I haven't used so far and I choose the one with the lowest cost, for example, to add it. One important thing here to keep in mind is that as we are building the solution piece by piece, please keep in mind that we have to maintain the feasibility. So for example, if I am looking for the minimum spanning tree, I cannot add the smallest weight edge if it creates a cycle, because then I no longer have a tree structure. Okay, so implicit in the algorithm when I'm talking about this is that when I'm looking in this second step here, when I say choose the next piece to be locally optimal, please think about it as of the ones that maintain a feasible solution. Okay, I cannot add again an edge to a minimum spanning tree to create a cycle, because we don't even care about optimality at that point. We have created a structure that's not even a tree. Who cares about its weight? Okay, so please keep that in mind. So we build the solutions piece by piece. We choose the next piece to be locally optimal among the available pieces. Now, one important thing I want you to keep in mind about greedy algorithms is that for many problems, greedy algorithms don't work. What do I mean by don't work? They don't give you the optimal solution. However, there are many important problems for which greedy algorithms work and actually give us a solution that has polynomial running time in the input size. Okay, so before we get into the details of specific problems, specific algorithms, and how we prove correctness of greedy algorithms, let us actually illustrate a couple of problems, 2 or 3 problems that are optimization problems and that greedy algorithms our natural way to think about the problem. Okay, so I will start with the first problem, problem 1. This problem is known as the change-making problem. Change-making problem. Change-making problem as in change for money. Okay, so imagine that you have you want to give change for a specific amount to some customer. Okay, so we want to give change. We want to give change in coins for a specific amount, n, and we have coins of certain denominations. We have coins of certain denominations. And let's say, for example, D1, denomination 1, it is greater than denomination 2, greater than denomination 3, and suppose we have M denominations. Okay, what is it that we want to do? We want to use the smallest number of coins. Okay, so we want to give we want the change. We want the change to involve the smallest number of coins possible. Okay, so again, you show up to a grocery store and you purchase something, and then they need to give you money back. Suppose they want to give you $13 back, and suppose they want to give you these $13 back in coins. Okay, so quarters, dimes, nickels, pennies, and so on. What is the smallest number of coins they can give you to give you that $13? Okay, so let's actually illustrate it with for example, with the coins that are used here in the United States. Okay, so we can think about the denomination. So D1, for example, is the quarter, which is 25 cents. Okay, D2 is the dime, which is 10 cents. D3 is the nickel, which is 5 cents. And D4 is the penny, which is 1 cent. Okay, so suppose we have these four coins, 4 denominations. And suppose now I want to give back, I want to give you change with these coins for the amount of 48 cents. Let's say N is 48 cents. So how many coins, what's the smallest number of coins can I give you here? So for example, if you look at this, I can give you 48 pennies. Okay, I can give you 48 pennies, and that will be the change. I can actually do something different. For example, I can give you what is it here? I can give you nine nickels and then 3 pennies, for example. So 9 plus 3, that's 12. Okay, so can we do better than that? Now, if you think about this problem and you think about the cashier at the store, they usually actually follow a greedy algorithm. So what would they do? They say, okay, 48 cents, let me give 1 coin of D1. Okay, 1 coin of denomination D1, which is 25 cents. I cannot give another quarter, because another quarter will make it 50, right? So I cannot give another quarter. So we have now 25. So when I have 25, now I have 23 cents left. I need to give 23 cents back. I cannot use quarters, but now I can use, for example, dimes. I can give you 2 dimes back, 2 D2. So now with D1, I have given you 25. With 2 coins, 2 dimes, I have given you 20. So that's 45. I still have to give you 3 cents back. I cannot use the nickel because it's 5. I can now use 3 pennies, right? So 3D4. So this is 3. And if you look at this, it is 48. So this is a greedy algorithm for this problem, where I started with the largest denomination. I gave you enough of this. to cover the change I need to give you. And then there is left over that I couldn't use this denomination for. Then I moved to the dimes. I gave you 2. I couldn't use more than 2 dimes. Then I went to nickels. I couldn't use nickels because the remainder is 3, and I cannot use a nickel for that. Then we went to pennies. I gave you 3. So here, if you look at it, how many coins did we use? If you look at it, we had 1 quarter, 2 dimes, and 3 pennies. So this is, we use 6 coins, right? Again, contrast this, for example, to use 48 pennies. Okay, 6 is much better than 48. You don't want your pocket to be full of pennies. 6 is much better than that. So this is a greedy algorithm for this problem. Okay, now, does this work? Is this guaranteed to be the optimal solution? If you give me these denominations, the 25, 10, 5, and 1, and you give me that n as input, so the input is the amount of change that I need to give you back, to an n equal 48 cents, for example. If you give me these denominations, this greedy algorithm actually works. It is correct, okay? No matter what n is, for this 4 denominations, this algorithm would work. Does it work in general? So what happens if someone changes the denominations? Let's look at a different example. Still use the same greedy approach, but use different denominations. Imagine the denominations now. D1 is 25, and D2 is 10, and D3 is 1, and N is 30. Okay, so if you think about this here, so these are the denominations we have. We don't have, in this case, for example, the nickel. We only have the quarter, the dime, and the penny. And the amount of change I need to give back is 30. If I use the same greedy approach by saying, let me start with the largest denomination, I will give you 1 D1. So this is now 25. And now I'm left with 5. Since I'm left with 5, I cannot use D2 because D2 is 10, right? So I need to give you 5 D3, okay, because this is 5 and 25 plus 5 is 30. And the number of coins I used in this case is 6 coins. Is this the optimal solution? The answer is no. There is another solution that actually gives me a smaller number of coins. You could have given me, or I could have given you 3 coins of a D2 or 3 dimes, and this would have basically be 30 cents, okay? So this is an example of what I mean by a greedy algorithm not working. We use the greedy algorithm to start with the largest denomination and give you as many of them as possible. Then we move on to the next denomination and give you as many as possible and move to the third and so on. The algorithm worked in the case when we had the 4 possible denominations, 25, 10, 5, 1. What does it mean to work? It means that I can write a theorem that says this greedy algorithm will always return the optimal solution. And in this case, in the top case, where we had these 4, we can write a mathematical theorem and write a mathematical proof to the theorem that this works. What does it mean for a greedy algorithm not to work? Again, in the second case, if I give you, I say that the 3 denominations are the quarter, the dime, and the penny. In this case, you claim that the greedy algorithm doesn't work. What it means doesn't work, you have to give a counter example like this. So you gave me, for example, n equal 30, and you say for n equal 30, then it doesn't work because the greedy algorithm would have told me to use 6 coins for the change, but an optimal solution here actually requires or involves 3 coins, okay? So this is an example of a greedy strategy. We are building the solution piece by piece. What do I mean by piece by piece? I first gave you, in the top case here, I told you, use D1. And then the second piece, I said, use D2. The third piece, I said, use D2 again. The fourth piece, I said, use D4. The fifth, I said, use D4. And the sixth, I said, use D4. So at every point, I am building, adding one more piece to the solution. And at every point, I am using the largest denomination that I can use. Okay, so when I have 23 cents left, I couldn't use D1, the quarter. So what is the largest denomination available to me? It's D2, and I can use it, and I used it twice, and so on. Okay, so greedy algorithm builds the solution step by step or piece by piece. Every time we use, when we are building the next piece, we are using what's available to us, and we choose the optimal of those. Again, here I'm trying to minimize the number of coins, and my greedy approach is to maximize the denomination I can use. Okay, and again, in this example here, I'm showing you two cases for the same problem. In one of them, where the greedy algorithm is guaranteed to work. So if I have these four denominations, D1, D2, D3, D4, the algorithm works. If somehow in the United States we do not use the nickel, then all of a sudden this greedy algorithm is not going to work. Okay, so let's look at another problem where greedy algorithm would be natural for it. So problem 2. Problem 2 is the problem of compatible intervals. Okay, so what is this problem? Imagine the input is in open intervals, A1, B1, A2, B2 to AN, BN. What do I mean by an interval? These are every interval is given by two real numbers. So A1 and B1 are two real numbers. And for example, 3 and 7. So this is the set of all real numbers between 3 and 7. When we say open, and we usually, when we talk about an open interval, we use parentheses. It means that A1 and B1 are not in the interval. Okay, so if you look at the real line, and this is 1 here and 3 here, if I use open circles here, this is the interval 1, 3. Okay, so I have n of these intervals, and think about these intervals corresponding to jobs. Okay, so for example, I have n jobs, and that I need to send to a printer or something like that, or I need to the operating system to deal with. And each job has its start time, which is given by the A, and finish time, which is given by the B. And what's the output here? We want to find the largest number of these intervals that no two of them overlap. Okay, the largest number of intervals such that no two of them overlap. Okay, overlap. Okay, why am I interested in this? Because again, imagine that I want to schedule all these jobs on one printer. I cannot make the printer print two jobs at the same time, right? So I want, if the first job starts at at 7 in the morning and ends at 7:30, and another job starts at 7:15, I cannot have these two printing at the same time. Okay, so we want the largest number of intervals such that no two of them overlap. So what are some greedy strategies here, greedy algorithms? For example, so we can have multiple greedy algorithms for the same problem. Okay, so one attempt is, sort the intervals in non-decreasing order of the AIs. Okay, so sort it based on a non-decreasing order, and then schedule or select intervals by their AIs such that no two overlap. Okay, so what do I mean by this? Schedule all these intervals and in an increasing order or non-decreasing order of the AIs here. So imagine that really the jobs are A1, B1, then A1 is smaller than A2, A2 is smaller than A3, and so on. So based on this greedy algorithm, I take A1, B1 first because A1, B1 has the smallest value of A1. Then I go to A2, B2. Suppose A2, B2 overlaps with A1, B1, then I ignore A2, B2. Then I go to A3, B3. If it does not overlap with A1, B1, then I take it. So we can actually visualize it. So imagine the intervals are like this. Something like this. So imagine that this is A1, B1, A2, B2, A3, B3, A4, B4, A5, B5. If you think about them, they are already sorted in increasing order. So A1 is before A2, before A3, A4, and A5, and so on. So based on this greedy algorithm, I would say, since I want to actually start with the non-decreasing order of the AIs, I will choose this. This is the first one I would choose. Then I will go to A2, B2 because it has the second smallest AI. I cannot choose that because it overlaps with this, right? So I mean, it overlaps here if you think about it. They overlap in this part. So I cannot choose this. Now I go to A3, B3. It doesn't overlap with A1, B1, so I can choose A3, B3. I can go now to A4, B4. I cannot choose it because it overlaps with A3, B3. I go to A5, B5. I cannot choose it because it overlaps with A3, B3. So the solution from here is A1, B1 and A3, B3. Okay, so based on this greedy algorithm, it is these two intervals that I can choose A1, B1 and A3, B3. Another greedy algorithm is not to choose or to sort based on the AIs and choose one, to sort based on the BIs. Okay, so I could choose based on the BI which one ends first, and then select them based on that. Now, if I look at this example that I just gave here, it will be the same solution, but I can draw a different example. I can draw a different example. So if this is A1, B1, A1, B1, and then we have A2, B2, and we have A3, B3, and then we have A4, B4. If you look at this example here, and I'm saying my greedy algorithm is, let's sort in non-decreasing order of the BIs now and choose based on that order. So if I sort them like this, B2 is the smallest value among all the BIs. So B2 is smaller than B1 and B3 and B4. So based on this new strategy, I can choose B1, A2, B2. Then the second thing is I look at the next BI, which is B4. B4 is smaller than B3 and B1, but A4, B4 overlaps with this, so I cannot choose it. Then I look at the next one, which is B3. B3 is smaller than B1, so I choose this one because it doesn't overlap with A2, B2. So in this case, the solution is A2, B2. The solution is A2, B2, and A3, B3. So this is another greedy algorithm for the very same problem. The first greedy algorithm was choose these intervals in non-decreasing order of their AIs, as long as, so the next piece that you add to the solution is the next interval in terms of its AI value, as long as it doesn't overlap. The second greedy algorithm is the same thing, but let's choose based on the value of BI in non-decreasing order. A third greedy algorithm for the very same problem is let's actually sort based on the length of the interval or the duration of this job. So let's actually sort them based on the BI minus AI. Okay, so in other words, we schedule the shorter intervals, or we select the shorter intervals before the longer intervals. Okay, so these are three different greedy algorithms for the same problem. Do they all work? Do they all guarantee an optimal solution? The answer is some of them do, some of them don't. And in this case, actually, if you choose based on the smallest AI, or if you choose based on the length of the interval, they are not guaranteed to give you an optimal solution. The second greedy algorithm I mentioned, where we choose based on the smaller or the smallest BI first, that is guaranteed to give us the optimal solution, and we can prove that mathematically. Okay? So this problem of compatible intervals, choosing compatible intervals, we want to minimize the number, we want to maximize the number of intervals we can choose, number of non-overlapping intervals we can choose. We have given three different greedy algorithms or three different greedy approaches to the problem. Two of them do not work, which means we can come up with a counterexample. We can come up with a set of intervals that when we run the greedy algorithm on them, it is not guaranteed to be the maximum number of intervals possible, because we can show what's the maximum number and we can show what the algorithm returned and show that the latter is smaller. And one of them works, which is choosing again by the value of in non-decreasing order of the value of BI for the intervals. That one is guaranteed to give us the optimal solution, and we can prove that mathematically. A third problem here, that third and fourth problems, actually I want to mention them together, is the third and fourth problem. Is the first one is the minimum spanning tree problem. Given an undirected graph, weighted undirected graph, and we want to find a spanning tree of that graph, so a tree that includes all the nodes in the graph and has the smallest weight. And the other one is the shortest paths problem, where I am given an undirected graph, for example, directed or undirected doesn't matter, but suppose it's undirected graph and some start node. The graph is weighted, there are weights on the edges, and I want to go from the start node, the given node, to every other node on the shortest possible path, where the length of a path is the sum of the weights of the edges on that path. These two problems lend themselves very nicely to greedy algorithms. And for example, for the minimum spanning tree, there is an algorithm known as Prim's algorithm. It is a greedy algorithm, and it basically says, let's start with a node. Let's start adding the smallest edge to that connects that node to something else, and then we move on to the next lightest edge and so on. For the shortest path, we have Dijkstra's algorithm, which works very similar to Prim's algorithm. And both of these algorithms are greedy algorithms. Both of them are correct. Both of them are polynomial and efficient. Okay, so in the next set of lectures, I will actually start zooming in on some of these problems and prove their correctness or argue why they are correct. Okay, but please keep in mind that when an algorithm is incorrect, as in a greedy algorithm does not guarantee to give us an optimal solution, the way to show that is by showing a counterexample. So for example, if you want to tell me Prim's algorithm doesn't work, you need to show me a weighted graph where Prim's algorithm returns a tree whose weight is x, and you show me another minimum spanning tree whose weight is y, and y is smaller than x, because now you have showed that Prim's algorithm chose a spanning tree whose weight is larger than another spanning tree, in which case basically we are showing that Prim's algorithm doesn't work. However, you will not be able to find such an example for Prim's algorithm and Dijkstra's algorithm, because we can write a mathematical theorem that establishes that Prim's algorithm is correct. Prim's algorithm is correct, Dijkstra's algorithm is correct. For the compatible intervals, choosing by the smallest b value of the intervals is correct, and we can prove these statements mathematically.